Well, welcome everybody. Lovely to see everyone here. And it's very beautiful here in Brighton today. So all of you from all over the world, welcome to our 7th RPA Computing Education Research Seminar of 2025. I'm Jane Waite and I'll be sharing the session today. And in this particular seminar series, we're focusing on teaching about AI and data science. And we're exploring the research that examines what students should learn about AI, machine learning and data science, as well as what might be the most effective ways to teach these really important topics in schools. I'm very excited today, and I know I'm always excited, but I am particularly excited today because we're welcoming 3 researchers today, so 3 for the price of 1. And when I saw their work at a symposium, a conference a little while ago, I was just mesmerized, blown away, just thought, this is it. There are all these components that come together, and I really think they've got something that is almost like some missing links in what we teach and how we might teach it. So thank you to Sarah Schoenbrodt from Salzburg University, Stephen Kindler and Martin Frank from Karlsruhe Institute of Technology, who are going to lead the seminar today on how to demystify AI. And although it says in the maths classroom, for me, it's just how to demystify AI in terms of exploring machine learning concepts with mathematics ideas. I'm so pleased to welcome our speakers, Sarah from Salzburg University, Stephen and Martin from Karlsruhe Institute of Technology. Sarah is an assistant professor of mathematics education. Her work focuses on bringing modern applications of mathematics and especially AI into school teaching. And she leads the computational and mathematical modelling program, and you'll see it CAMP, CAMMP, in Salzburg, to give high school students insights into the relevance of modern mathematics. Stephen Kindler is a PhD student at Karlsruhe Institute of Technology, and he's researching how to teach artificial neural networks effectively. And alongside his doctoral studies, he develops learning materials and contributes to CAMP. Martin Frank is a professor of computational science and mathematical methods at KIT, that's much easier to say, and director of the Scientific Computing Centre. He founded the CAMP Education Lab and conducts research on mathematical methods, including AI, as well as mathematics education. And in today's session, the 3 of them will be exploring how machine learning concepts can be integrated into high school mathematics education. And for me, it's also seeing how that overlaps with how we teach machine learning in computer science. And they'll be sharing strategies and resources for teaching the mathematical foundations of AI and discussing how these approaches can make abstract concepts like neural networks more accessible and engaging for students. We're all really looking forward to hearing their insights. So over to you guys.
Welcome from our side. Let me just directly dive into the topic of demystifying AI in the math classroom and our approaches and teaching concepts we developed and also tried out several times with high school students to make the math behind machine learning actually accessible. This is joint work between Stefan, myself, and Martin. Martin is also in the chat. He's or in the conference. He's not going to present, but I guess he will be able to contribute to the Q&A session afterwards. So I need to. Yeah, wait. Perfect. AI technologies are nowadays, influencing young students' lives basically in every area. And this is why we really need to empower students, young students, high school students at an early age to critically, reflectively, and creatively engage with AI technologies. And what we need in order to achieve this, we need early AI education. And AI education, which both focuses on the opportunities and design possibilities and the limitations. And this, in the last point, which is quite important in our opinion, also on how AI actually works. Because once you understood how these technologies work and how the mechanisms and methods underlying these technologies actually work, it makes it so much easier to reflect on the opportunities and on the limitations of these tools and use them in a responsible way. When it comes to how AI actually works and understanding how AI technologies actually works, our hypothesis is that the mathematics classroom, that mathematics education can play a very important role in this. And the three aspects we want to shed light on today and kind of want to convince you of, and maybe also discuss in the end, is that yes, it is reasonable and it is possible to include AI education into the mathematics classroom or in math education. And later on, we might be able to discuss if it's also necessary. So why is it reasonable to include it into mathematics education? Well, the first and most important aspect is that machine learning methods are mainly based on mathematics and data. And when I talk about mathematics within this talk, I mean mathematics and statistics. So statistics as a part of mathematics, because in Germany and also in Austria, there's not a special subject for statistics, but statistics is included into the mathematics curriculum. Second, yes, it is certainly possible to do it in a math classroom because, or it is certainly possible to give an authentic insight to high school students already on the mathematical basis of machine learning methods. Why? Because there's so many different connections to school mathematical contents when you look at the elementary descriptions of these methods. And this is really nice and gives the opportunity to look at this from a mathematical perspective. And last but not least, which is also important, is that there exists a variety of suitable real world and also relevant to the students problems out there that we can use to develop engaging teaching and learning material. So our main hypothesis for this talk is, yes, math education is an essential component for developing AI skills, and we would love to discuss this hypothesis in the end with you, after showing how we do this and which kind of teaching and learning material we use in order to work on the math side of AI. We are not the only ones stating or showing that mathematics education might be a good place also for AI education, but there are several other authors and research projects that already worked on making the mathematical backgrounds of different machine learning methods accessible to students and also especially to high school students. This is just a selection of some papers. There's, I guess, a bit more out there nowadays. But compared to what's going on in computer science education, when it comes to AI education, this is not really much what's going on in the math education community or research community. So there's still work to do, kind of. I would like to, or we will show you and give you an insight in different teaching and learning concepts and materials we use. But before doing so, I would like to, look at the typical math terms and the typical ways of describing the problem behind machine learning from a mathematical perspective. So we use the same, or we are on the same. We look on the problems which we tackle in the following from the same perspective. So the starting point when it comes to developing a machine learning method in order to develop an AI application is, in most cases, in most modern cases, data. And this data consists of input data and output data when it comes to supervised learning. In the most simple case of imagining the data, how it might look like, can be seen in this two-dimensional plot. So we have just one input variable and one output variable. And the main goal when it comes to developing an AI system based on supervised machine learning from a mathematical perspective is kind of developing or finding a mathematical model that best describes the unknown relationship between the input and the output data. And to formulate it in a even more mathematical way, this often, or in most cases, means that we try to find a mathematical function that in such a way that the predictions, so the function values when entering an input, are very close to the known outputs yi. And this is a mathematical description of many problems underlying AI technologies, which are then solved in different ways. When we will look at the learning material in a second, we will also look at different problem classes that are underlying different AI technologies. And the main differentiation relies on the nature of the output, yi. If the output is categorical, we end up with a classification problem. If it's numerical, we end up with a regression problem. And both of these problem classes, or for both of these problem classes, we developed teaching and learning material with different focus. And yeah, I would like to directly dive into that right now, starting with the classification problem. So our focus today, so for the rest of the talk, is we would really like to give you a practical insight in what we do with the students and which kind of mathematical aspects the students discover when it comes to working on machine learning. First, I will dive into a workshop on image classification, and here the focus is on the machine learning methods, the support vector machine. And then I will hand over to Stefan, who will then give you an insight in a learning path to better understand artificial neural networks from a focusing on the mathematical parts of this. And we will end with some conclusion about what we're going to present here. The focus of our presentation will not be that much empirical, but more from the practical perspective. So how does the teaching concepts look like, and what do we actually do there with the students? Although we performed and used this material quite a lot with high school students already. The workshops and also the teaching and learning material was developed within a so-called computational mathematical modeling program, CAMMP, which is some kind of education laboratory where students work on different real-world problems. And the main goal of CAMMP is to allow students to solve authentic, real-world and relevant problems using mathematical modeling and computers. And one idea of this is also really to show students that the mathematics that they learn in high schools are actually used for something. So they are actually used in our society, in our economy, in technology, and so on. So really let them experience the role mathematics has for our society. In order to achieve this goal, we develop teaching and learning materials with one focus on AI, but also on other topics as well. For example, renewable energies. We perform workshops, in most cases one-day workshops, where students or classes of students come to the university and where we then run through one of these topics together with them. And we do this at different locations in Germany and in Austria. Here you can see a subsection of all these AI workshops we developed. So in black, you can always see the real world problem, so to say, the students work on. So for example, here they work on, in one workshop, they develop a recommender system for movies based on a data set from Netflix. And in blue, you can always see the machine learning method they develop step by step, so guided through didactically reduced versions of the mathematical background and using appropriate teaching and learning material. I will focus now on the image classification based on the support vector machine. However, all the other materials for the other workshops do follow the same design principles. Okay, now let's jump into the image classification workshop. and the teaching and learning material on the support vector machine. This workshop was designed for upper secondary students, and you will, I guess you will see in a second why, because the math is embedded in the curriculum in this level. The starting point for this teaching and learning material is the problem of classifying images of traffic lights into red and green. And as images are quite complex data for students, also for upper secondary students, we reduce this problem heavily by assuming or just picking one pixel from the upper light and one pixel from the lower light. Then we end up with this representation here, the red-green representation of the traffic light. And to even simplify it further, we transform it into a grayscale picture or image. And we end up for each traffic light with a two-dimensional data point. And this is something students at high school level can actually work with. In the plot on the right, you can see several data points. These are, each data point represents one image of a traffic light. And this is basically the starting point. It's the training data, where we want to develop a classification model that then can classify new images of new traffic lights. The idea of the support vector machine, I don't know if you're familiar with this or with that or not. If not, that's absolutely no problem, because I will run you through the main ideas right now. And basically the things the students do. The main idea here is that you want to find a line find a line that separates the data points of both classes. And once you found a line that does this, so the separation, you can use the line to classify new data by just looking on which side of the line the data point lies. When you look at this picture, you can already see that there exist many lines that do the job, so separate the data. The question is, which one is the best? And in order to answer this, we can have a look at this black data point here, and we see that the green line, which is quite close to the red data points, is kind of misclassifying this data point because the data point is quite close to the red data points, and it might be a red traffic light, but the green line is too close to the red data points, so we might get a misclassification here. And the support vector machine mainly builds on this idea that we try to choose the line that maximizes the distance between the data, all the data points and the line. So maximize the data point free area, basically. In order to find the line that actually does this, so the line that maximizes this distance or this data point free area, also called margin, first of all, we need a mathematical representation of the line. We need to compute the distance of all or any point to the line to then maximize this distance. And this is the things the students then also do on a mathematical side. So they describe the line mathematically using the actual formulation, which is also in use when it comes to the support vector machine, which is the point normal form or normal vector form, which I don't know which term is the one you're most familiar with. You can see it here in this plot on the right side. So we have a normal vector and a supporting vector P, and this is the description we use in upper secondary education. We do this because this is actually embedded in the curricula, both in Austria and in Germany, for mathematics education. In order to find the best line, we need to define what means best. And I already said this. We choose the line with maximum distance to the nearest data points of both classes. And in order to find this line, we have to calculate the distance of any data point to the line. And this computing distances from points to lines or points to planes is something students also have to do extensively in the mathematics classroom at upper secondary education. So this is another application of what is already in the curriculum, basically. Once we found the optimal line, we still have to go one more step to actually classify new data points. Because we don't just want to look at the plot and see if a data point is above or below, but we really want to compute it automatically. And here another very relevant school mathematical content comes into play, which is the dot product or scalar product, dot product, I guess. And also here, I won't state any formulas, but what the students actually do is they come up with a case distinction, and you can understand what the students do by just looking at the plot. The students look at the angle between this normal vector and this connecting vector between any data point x, e, and p, so these two vectors. And when you look at this angle, they point in the same, when they point in the same direction, the angle is not smaller than 90 degrees, and the dot products leads to a value smaller than 0. And if the angle is bigger than 90, then the value is smaller than 0. So either bigger or smaller than 0, and this leads to a case distinction. And this is another application of school math here. Last but not least, I forgot to mention at this point, so when finding the optimal line, we want the students to formulate the distance from any point to the line, but what we don't want the students to do is to solve the optimization problem. This is something which is done using the computer as a black box. So this is also quite important to mention. Once we developed our mathematical model to classify data, we still have to somehow validate if the model is actually useful also to classify new and unknown data points. And there we typically also use test data, and the students work with contingency tables to use the mathematical, or the term that is typically used in mathematics classrooms, but to use the machine learning slang, this would be a confusion matrix, but also something that's already there in the curriculum. The last aspect is then discussing limitations. So the last step in this learning trajectory, where we discuss that the data sets are often not as neatly as linearly separable as I presented in the beginning. So this is leads to some limitations which are quite important. For example, in this picture you can see, or in this plot you can see that they are already in the training data, that there are data points overlapping, so you will already have some data points on the wrong side of the line. The reason why I really like the support vector machine so much for the math classroom is that it can really be nicely translated from the two-dimensional space to the three-dimensional space. And we can do this by just adding another traffic light, so another light from the traffic light. So now we have 3 lights, and we end up with three-dimensional data, as you can see in here. And the mathematical description of everything we did before stays the same. The only thing we look at right now is no longer a separating line, but a plane. And the description of the plane is exactly the same as for the line. So you can use the normal vector form. You can use the very same formula for the distance and also the dot product in the very same way. So it really translates from 2 dimensions to 3 dimensions. And later on, you can also apply it to n dimensions, so really bigger pictures. Pictures with, or images with more pixels, basically. I hope I could show that in this example, there's a lot of school mathematics going on, at least from the curricula in Germany and Austria. And lots of these contents come from the area of analytical geometry. So lines, planes, distances, and the dot product. And this is a nice opportunity to actually show students that the mathematics they learn in school are actually in use when it comes to technology, society, economy, and so on. Just to give you a counter example, here's a glance into a textbook from a German a German textbook, a German school. I just screenshotted the pictures from the tasks, but I think you can imagine what's going on there. So they also have to do lots of things with lines, planes, distances from points to planes, and so on. And when looking at these examples, it's not very surprising that students might ask why and where is all this math actually used for. And the support vector of a machine really gives a nice opportunity to show that. Last but not least, we also include in the workshops we develop in the material, we try to include critical discussions, both for when it comes to ethical aspects and also when it comes to the relation between the applicability of the AI tool and the mathematical model. To give you an example, looking back at the traffic light problem, one might argue that isn't it more problematic to run through a red traffic light instead of stopping at a green one? And wouldn't that mean that we shift the line a lot closer to the green data points to make sure we never run through a red traffic light? And this would also change the mathematical model then. So, but this could certainly be argued by someone as well. Before I hand over to Stefan, who will then jump into the neural networks, let me just quickly show you how the teaching and learning material actually looks like, that we developed both for this workshop and all the others that I mentioned before. The material focuses on the mathematical background of the machine learning application. So we developed it in a way that no programming skills are needed. We use Jupyter notebooks to develop these worksheets, and we host it on a Jupyter Hub server, so the students can just access the material via a web browser, and they don't have to install any software or anything. Then when the students work on the task, they get a direct feedback on their solution. So they enter their solution and get a feedback if it's correct or not. And sometimes they also get a hint where they might have made a mistake when developing a certain mathematical formula, for example. There are staggered hints included that the students can access when working on the worksheets. So if they don't or get stuck with the tasks, they might find a hint so they can still work on this on their own. But to make this a bit more transparent for you, how this actually looks like, I will show you one short video of this. So in order to not need programming skills, I quickly stop. We use this fill in the gap approach. So within the code fields of the Jupyter notebooks. So here's the task, basically, in blue. And then there's the code field where the students have to complete the task. And then the fill in the gap approach is implemented in a way that the students only have to replace these nones, basically, with their solution. And then on the first worksheet, the students should get familiar with images and start by producing their own red and green traffic lights. You can see this now. Here's the direct feedback. Now we enter the solution, and in this case, the students get a visual feedback. So they see, okay, this is actually a red traffic light. Then they, in this case, have to transform the images to grayscale values. They enter the formula and get a direct feedback on that. There are also lots of different plots included and visualizations. Here, for example, we have an interactive plot to choose the optimal separating line and to argue why this is actually optimal. Then there are certain answer fields where the students can save their solutions, and the solutions can then be used in the discussion phases in between the workshops to discuss what they came up with, basically. And here on the left, next to the video, you can also see how it looks like if we include a hint or a tip for a certain task.
thank you very much, Sarah, and hello from me as well. And now I'm going to talk about a learning path to better understand artificial neural networks. Artificial neural networks are big and powerful, and they are the basis of many AI applications like chatbots, ChatGPT and Gemini and so on, image generations, but also for weather forecasts in medicine and so on. And since they're used so often, I find it very interesting to have a deeper look or a closer look onto them. But soon you realize, okay, they're very complex and very large, too complex to talk with students about the big models. So the first step we do is we are not focusing on generative AI like the chatbots, but we focus on regression models, for example, the weather forecast. Because when you have to talk about, okay, output that is like text or pictures, it's more complicated than, for example, in the weather forecast, if you want to predict the temperature or the pressure, then this is something easier and it's something that you can work with. And even so, with current models from chatbots having like trillions of parameters, even the weather forecast models have have like 64 million times 4 parameters. And the structure here, I don't want to show it too long, is still very complex. So what we do is we simplify it down. So we look at a very small artificial neural network and which has one input, 3 nodes and 1 output. And with this, we want to tackle common misconceptions. So what we hear is, okay, the ANN can learn physics. Even the verb learning we think is wrong or misused. It can recognize patterns. It also works on data it has not seen yet and is way too complex to understand. And what we want to do is we want to explore the functionality of this toy network and thus explore the functionality of bigger networks as well and demystify misconceptions. We can't demystify everything and we can't answer everything. For example, we can say how it works, but we can't say why it works. This is still like ongoing research and the mathematicians can't really say it yet. So that's still something we want to work on, or there it needs to be worked on. The learning path starts with looking at one single node, and this node has one input and one output, and can be described as a mathematical function. And this mathematical function, the graph of this mathematical function looks like this, and it's basically the concatenation of 2 functions, a linear function with 2 parameters, w and b, and activation function, which normally is a nonlinear function. And what we look at is the logistic function, which is basically next exponential function. Yeah, and what students do here, they can look at this, and I will just switch to this. As Sarah told us, we have interactive material in our workshops, and here they can experience and explore for themselves what the influence of the parameters is. So if we change this W, then we see, okay, the slope of the graph is changing, and basically we are stretching and we're stretching it in the X dimension. And if we change the B, then we are moving it in this direction from left to right. And having explored it, students can then talk about this, and they can do a so-called Kurvendiskussion. So that's a German term, and basically it means function analysis. So they treat it as a normal function, which they do in school mathematics anyways. and they can use the mathematical tools they learn in the normal curricula. And so they can talk about the domain and codomain. So for example, okay, you can't get any value smaller than 0 or bigger than 1. And you can also talk about the limits. Okay, what happens if we enter a very large X, then we get most likely we get 1 as a result, or 0 depending on the W. And we can talk about extremes or the lack thereof. So it's just a monotone growing function. There are no extremes, and you can talk about the parameters of the influence of the parameters W and B. And now, using this, having the students get familiar with the functions or with one function, we talk about the whole network. And the whole network is here defined as the weighted sum of 3 of those previously considered functions. So this K1 here, this is like the function we looked at, and there's one parameter in front of it, and then we just add it up and add also some other parameters. And here I also want to switch to this again. So here you can check out the whole network. So basically, this is the one node we have. So we have the input and then one node, and then you can change the parameters around. And then you have another node, the orange one, and then you can also change it accordingly, change the weights here. And what we then do is we add those up. So we add those up and we get the resulting graph of the function, and this is the black line. And then we can see, okay, what happens if I change the parameters? What happens to the output of this network? And as you can see here, okay, we get extremes as before we didn't get extremes, now we have them. And if we add a third function, then we can get more complicated structures. And here students can also do the function analysis or the Kurvendiskussion, and they can talk about, okay, now we have extremes. They can still talk about the limits of the functions, and they can have a discussion about all the possibilities that are or the possibility that this network brings. And they see, okay, this is very flexible, and you can have very different graphs produced by this. And after this part, students are able to formulate this toy network as a mathematical function. They know about, okay, the flexibility, know about the influence of each parameters. And now we want to show them basically application of this. And now coming back to the basic problem is we have a regression problem, and I'd already talked about the weather prediction. This is obviously way too complicated, but as Sarah told us before, the goal of mathematical modeling is to describe an unknown relationship between input and output data. So we have data, and we think, or we know that there's some relationship between some features of this data set, and we want to use the network to model this. And we do this as a regression problem. For example, you could think about, okay, all the information about pressure, about what the temperature was yesterday, about the wind and everything could be used to predict the temperature. And so this is the idea, but we simplify it even more because we only have one input data. We just want to use it to approximate the trend that is given by a sine curve. And students can now use this network and their knowledge about the network to say or to see if the model can be used to actually approximate this. And obviously we can create two extremes. And these data points can actually be fitted with the given network. But if you zoom out, you can see that, okay, if we look further into the future or the past, then the function converges and it doesn't work anymore. So it's not continuing the scribbles or the periodic function. And if we have more functions, then we have a problem because our network cannot solve this. We only have a limited amount of extremes that we can create. So then the students can answer the question, okay, how can we modify the network for this task? And usually they get to the answer that, okay, yeah, just add more functions. And this is the case. You can, if we change the network structure to a 161 structure, then this task is possible. And at this level, it's too complicated to do it manually. So as a black box, the students are introduced to an optimization algorithm that actually chooses the parameters for them. But they have to give define the structure of the network. And another problem that you could look at is, okay, now we have multiple periods of the sine function, but there's some missing data in between. And the optimization algorithm finds these the parameter or chooses values for the parameters such that all the data points are fitted, but in between and outside it's not doing a very good job, meaning that, okay, there is no it didn't understand how this relationship is actually working. And if you look here, we have a 1501 network structure, so it would be possible to do more, to simulate or model it in a better way. And what can students actually learn from this? They recognize ANN as a highly adjustable function, as a mathematical function, meaning by adding nodes, any function can be approximated as precisely as desired, but only on a bounded set. And the function can approximate relationships in given data, but it only works in the interval in which the data points are given. And this concludes that the ANN model doesn't understand, and it doesn't even know when it doesn't know. If you look at this graph, the output or the network in the end is just this red line. So if I plug in like -10, it gives out a value -17, but it doesn't even know if this is something where there was data that it was optimized on or not. So yeah, it is not able, it doesn't know stuff. And at the same time, from a mathematical point of view, the students develop and train mathematical skills that are present in the curriculum anyways. And to come to the conclusion, in both our model, or in both of the presented ways, and normally in all our workshops, we have a black box and white box combination, and we try to model these approaches. So for both of the things that we presented today, the optimization algorithm is actually a black box. We don't talk about it. We just talk about, okay, what's the task for the optimization algorithm. But we talk more about the mathematical description of the models. And to come to the last slide, almost the last slide, to the initial statement of ours, we think that AI education in math classroom has mutual benefits, and so the AI education can profit from it, and students are able to have a deeper understanding of the results of AI models, have a realistic assessment of the opportunities and risks, and get an understanding of the human role in development of these AI models. And at the other time, students can see, okay, math is actually something that's very important for modern applications. And at the same time, they develop and train the mathematical skills and see the links to other school subjects or to other subjects in general. Okay, this is our statement. And yeah, we also have literature, of course. You can see it in the slides if they're uploaded. But at this point, we want to say thank you and are looking forward to a lively discussion.
So we give a round of applause, and now everybody's minds are going. Thank you so much to the team for coming and presenting. Thank you for all of you for staying. And I've got to do my little bit at the end. So on the 9th of September, we've got Matti Teedri. He's coming back from the University of Finland to talk about Sommerkönig. We love this tool. It is the best tool ever. That really is very good at black boxing certain things and revealing certain things. So please do come along to that next one and have a lovely morning, evening, or wherever your time kind of is. And if you want to turn your mic on, you can and say goodbye or au revoir or whatever language you're in.